So to finish talking about post-war skyscrapers, I want to look at a couple of really famous ones in Chicago that come out of this experimentation, both in tube structures that Fazler Khan, Myron Goldsmith, and Bruce Graham were exploring at SOM, and increasingly the research that was going on south of the Loop at IIT. Mies left IIT in the late 1950s. He designed Crown Hall, but was soon after kind of forced out because of university politics. But the program at IIT continued to be a sort of laboratory, sort of think tank that went hand in hand with some of the design work that was going on downtown. IIT sent graduates to most of the big firms in the Loop, but the firms there also began sending people down to IIT both to teach and increasingly to lead thesis projects, a couple of which you see here. The pedagogy of the graduate program there was certainly about experimenting with new structural forms, not only for their efficiency, their ability to gain greater leverage over the resources that were to hand, but also to think about the architectural expressions that could come out of these. And in these three, you see that there's definitely a lingering Mies influence, a preference for kind of minimal detailing, things that align, grids that are adhered to really, really rigidly, but also more experimentation beyond the kind of curtain walls and sort of simple, fairly simple grids that Mies was arguing for. One project in particular, a skyscraper project by a Japanese student named Mikio Sasaki, would prove to be really influential. Fazler Khan and Myron Goldsmith both taught at IIT in addition to working at SOM, and they were very open about ideas going back and forth, that they would work with students on concepts at IIT. Those concepts would often emerge back in the office at SOM. Goldsmith and Fazler Khan were both advisors on this project in 1962, and if it looks familiar, it should, because it came right before one of SOM's greatest skyscraper works, the John Hancock Center, which was built in the late 60s, so just a couple of years later. Sasaki's thesis, as you can see, explored the idea of using cross-bracing, a technique that we looked at when we looked at 19th century skyscrapers. Early steel high-rises used cross-bracing as a method of wind bracing. And here you see that cross-bracing not buried in the center of the building as it was in a typical 19th century skyscraper, but located actually on the exterior. Architecturally, that becomes part of the building's expression, but given what we know about tube structures, it's also very importantly now making the kind of exterior bearing wall, if you like, even more efficient, right? Creating a hollow tube that now is using even less material instead of the stiff moment connections that Kahn and Goldsmith used at Brunswick, or that Kahn and Graham used at Chestnut DeWitt. Here making the exterior bearing wall out of steel and reinforcing it with this cross-bracing principle that eliminates a lot of the extra material that has to go into a moment frame. The Hancock has, of course, not only the cross braces, but it has this very signature form, right? It tapers as it rises. And that, as you can see on the right, creates floor plates of many, many different sizes, right? About 100 different floor plates, all of them varying dimensions. The cleverness of the project has to do not only with the fact that the taper is a very efficient wind form, right? It resists wind by having basically a big footprint, or if you like, a deep root at the cantilever, tapering up to the top. So it's lessening the sail area toward the top of the building where it has the greatest bending moment, and it's maximizing the footprint down at the base where it has the greatest resisting moment. That taper, though, also comes about from the program, which was originally for two buildings, one of them a commercial office building, one of them a residential apartment building. The site proved to be too crowded to get two 50-story towers on it comfortably, and Graham recalls a meeting where they just decided to take the apartment tower and put it on top of the office building. Apartments tend to have narrower floor plates because there's a premium on rooms that have adjacency to views. Offices tend to have wider floor plates. Administrative offices, executive offices want or get to have windows. Clerical offices often are open plan that are removed from the windows, so office floor plates can be deeper. Deeper still, you can have car parking, and beyond that, you can have also department stores, which really only need show windows, right? Don't need daylight at all at this point. And if you look, you can see some divisions. The text is a little hard to read at this scale. But basically what SOM decides is that up in this part of the building are going to be the apartments where the building gets narrower. There is then going to be an office tower basically down here. And at the base, you have car parking and the department store. In between, down at the bottom, you have retail, other retail, and ways to get up to the car park. At the very top, you have a restaurant, observation deck, the things that we expect to see at the top of a skyscraper. And then right here in the middle, at the base of the apartment tower, you have a sky lobby where the apartment dwellers have a swimming pool and their own kind of convenience shopping, so they don't have to run all the way down to the ground to get a bottle of milk. Here you can see the section juxtaposed against plans. The problem, of course, is that the office has to draw a different plan basically for every single floor, right? Every single dimension is different. And with the cross bracing, of course, you have to make sure that the steel that is in those cross braces lines up precisely with both the adjacent steel and with the floor plates. So it's a problem of coordination, and it becomes a problem of calculation as well. They can massage the dimensions a little bit, right? The offices on the top are just a little bit too narrow for premium office space. The apartments on the bottom of the apartment level are a little too deep for premium apartment space. They have a couple of different apartment layouts where they mix and match studio versus 2-bedroom and 3-bedroom to take advantage of the proportions they have. And as you can see down at the bottom, the really clever thing is right as the building gets wide enough to have double row parking on either side of the core, the parking kind of enters in. So everything is perfectly tuned to the one shape that they have. Kahn and his engineering team have to go to various universities to borrow computer time to run all of the calculations it takes to figure out how the cross bracing is going to work. If you think about it, the advantage of a steel frame is that you're talking about various elements, and you can go in and kind of size those elements based on how you see the load flowing from slab to beam to girder to column to foundation. The cross bracing on the Hancock, though, isn't just wind bracing. It's also integral with the floor beams and with the columns. And what Kahn and SOM's engineers discover is that those cross braces also distribute all of the loads in very complex ways. So it makes the steel structure into a hyperstatic monolithic structure. This is difficult to calculate, but it gives an added efficiency. And as you see on the far right, this graph that shows the weight of steel per square foot of rental space versus the number of stories, you can see that the Hancock is just wildly off the chart, right? That it is both the tallest and most efficient building or skyscraper of the era, right? It has the same pounds per square foot as a building that is less than half its size, right? U.S. Steel in Pittsburgh or Alcoa in Pittsburgh, one of the ones we looked at. And you can see Inland Steel way down there at the bottom, right? Almost at the bottom. Those moment frames that Kahn had designed just 10 years before the Hancock meant that the Inland Steel building was far less efficient, smaller building, so it should have been able to use less steel per square foot, but in fact it used much, much more than the Hancock. The construction process, like many of these, was its own kind of exercise in efficiency and scheduling. And you can see both the kind of state-of-the-art in tower cranes that are climbing the outside of the structure as it goes up. The steel was all fabricated in Gary, just down the lake, and brought to the site by both truck and boat. And then in the center, you can see the kind of scale of the operation. Those diagonals come into these huge gusset plates that basically take the loads, which could be tension, could be compression in those cross braces, into these kind of massive 3 or 4 foot deep W shapes that then go into the ground and into the foundation. And on the right, you see the detailing, which is all in aluminum. So all of the steel work is covered. It has to be both fire protected, but it also has to be thermally insulated. And they detail this very, very minimalist aluminum skin that still expresses the geometry of the static solution, right? So you still get the sense that the cross braces are coming into a gusset plate of sorts, and those forces are being resolved by the column and by the girders surrounding them. You can also see there's a direct Mies tribute. You can see one lonely I-beam on the outside of the column covers. Those function as window washing rails, but they also, I think, are a direct homage to Mies. Mies died in 1969, but the discipleship of SOM certainly lives on, and that seems to be kind of a signature piece, right, that they borrow from his apartment buildings. So shortly after the Hancock is open, the Sears Roebuck Company, which is a longtime Chicago retail firm, comes to SOM and asks them to design a 4 million square foot headquarters building. Sears will take about half of the building, and then they want to lease the rest of it out as an income-producing property. There's an interesting kind of story where after the Hancock gets produced, it is so efficient, so successful, so iconic. Bruce Graham, in a published interview, says, this is the only solution you could really come up with, right? It's the ideal solution. Every building over 1,000 feet is going to look like this. And when Sears hires SOM, they hire them for their super high-rise expertise. They want a building that is 1,000 feet or more. It ends up being 1,400 feet. But they tell them that they don't want another Hancock, that the Hancock is too iconic. And in fact, they want a building that's going to be distinctive on the skyline in other ways. So Kahn basically has the opposite problem, right? How do you take a super tall building, 1,400 feet tall, and how do you find an effective and efficient enough solution that isn't like the one you just did, right? Which everyone acknowledges is kind of the ideal static solution. And what Kahn does is he goes back to that idea of Goldsmith's, that every height of building has a kind of ideal form. And if the trussed tube of the Hancock isn't kind of allowable, then Kahn goes to what the next level up would be, which is called a bundled tube. And there are two ways to think about this. One is that Sears is 9 tubes that are attached to one another that reinforce each other. You can think about it like 9 drinking straws that you tie together that collectively will be much stronger, much more resistant to buckling than just one, or the 9 that aren't tied together. Or you can think about Sears as one giant tube that actually has 4 shear walls that cross brace it, that keep the tube's walls from buckling on their own. And in the lower floor plan, you can see this quite clearly, right? Here's the exterior tube, and then the 4 shear walls are basically built of what look like Virendale trusses, right? Giant columns, giant girders, but they leave these large 75 by 75 areas open for offices. The other way to look at it is that is one tube, and it is braced by all of the tubes around it. So they function basically like those tied straws. And any structure, like the kind of rule of thumb is if you can explain the structure in more than one way, then it probably has redundancy. And it's probably not only going to be safe, but it's also going to be fairly efficient. You can see that the tubes step back as the building rises. The biggest bending moment, of course, is going to be toward the base or the root of the cantilever as it resists wind. As you go up, a couple of things happen. Like the Hancock, the need for large floor plates changes. Sears is going to take the lower half. They don't care how far their employees are from windows. The executives get the windows. Everyone else gets kind of open floor clerical space. But as you go up, when the speculative offices take over about halfway up, well, there you're trying to let out prestige space, and so there you do need more windows. So as you can see, the intermediate floor, the Greek cross shape, has windows all around the perimeter, so a much, much higher perimeter to area ratio. Therefore, many, many more offices have windows. And then in the very top floor, 2 of the tubes continue all the way up to 1,400 feet. And those are the real high prestige firms, right, where you kind of open the elevator doors and the curtain wall is sort of right there. Everyone has a view. And at the top of the building, of course, those views are going to be the best. Tapering the building, even in this blocky fashion, also reduces the amount of sail area at the top. And if you squint at it, you can see that the building does have a wider footprint at the base, right? Like the Hancock, it spreads out at the base, so it has a greater resisting moment to wind. So the structure is a reasonably efficient one. Kahn goes exactly the opposite direction from the Hancock. And instead of doing cross bracing, he reverts to a moment frame. And the entirety of the Sears structure, all of those 9 bundled tubes, are built like the torque boxes at Inland Steel. They are moment connections between oversized columns, oversized girders. And what that does is it creates thousands of stiff joints throughout the structure that collectively give the building its stiffness, its rigidity against wind. This is a material-intensive way to brace a tall skyscraper. But Chicago is a steel city. Steel is relatively cheap in the 1970s. Inflation is very high, and therefore there's a desire to find ways that the building can go up very quickly. And steel, because it can be prefabricated while foundation work is going on, steel helps you telescope the amount of construction time. And the erection time for steel, of course, is much quicker because you're not waiting for each floor to cure before you can go up and form the next floor as you do in concrete. The structure is clever, but again, like the Hancock, the construction process was maybe more clever. The contractors on the job figured out, along with Kahn and his engineers, how to take each one of those moment connections and weld them up in the shop in panels that they referred to as Christmas trees. You see a Christmas tree on the truck on the left. Those Christmas trees could be craned into place and very simply bolted to adjacent Christmas trees at the midspan of what would become the girder. So if you look at the structural diagram here, there's a column, there's a girder, and you can see that the Christmas tree is shaped like this, so 2 stories tall. All of these joints around the torque box are welded in the shop so they can be inspected. They have kind of factory conditions that they're made under. And then the Christmas trees are connected with bolt connections at their midspan, where the bending moment is going to be greatest, but the shear is going to be least. In here, you can see also that the shop fabrication includes cutting these big holes in the girder around the neutral axis. And that is so that mechanical systems can be threaded through later. And they are cut in every single piece because the project is fast-tracked. And this means that the structural package goes out before the mechanical package is finished. Today we do this all the time. We have building information modeling that we use to keep track of things. This is all on a project where the drawings are all done by hand. And telescoping things like that seems a little bit risky. So the solution is to just open up the structure wherever you can, and even if not every one of those holes gets a duct in it eventually, it means that the mechanical engineers, while the building is being fabricated and even built, the mechanical engineers can come in and with some reliability lay out their ducts, knowing that they will have access through the girders. John Zills, one of the engineers at SOM, remembers at some point realizing that these Christmas trees were so heavy that they would not only have to do a sort of typical thing in Chicago, which is looking at the height of one of the trees on a flatbed truck and making sure it can get under all of the bridges between Gary and the job site. He also remembers having to go through and calculating the load on all of the bridges that the truck would go over and making sure that the Chicago streets would be able to take the heavy load of these moment frames being trucked piece by piece through the city. Here on the left, you see kind of finished product. Within those tubes, you can see open web steel joists that are forming the 75-foot spans of the floor. So enormous open office spaces. framed by the kind of march of these columns at 75-foot intervals, forming the walls of the bundled tube, or if you like, the shear walls that are bracing the perimeter tube itself. And on the right, you see Sears beating out the Hancock finally for tallest building, not only in Chicago, but beating out the Empire State Building for tallest building on the planet, a record it held for either 25 or 30 years, depending on who you believe. We looked at modeling a lot of these buildings, as I said in the previous lecture, BART. And here you can see a little more clearly how the bundled tube interacts with the interior. You can see the core rising up in the center of tube, but also kind of spilling out in the lower floors into adjacent bays. So the elevators, note, do not have shear walls around them. The elevators are just enclosed by fireproof gypsum wallboard. All of the building stiffness is taken up by these oversized girders and the oversized columns. And as you see on the exterior, that kind of deep spandrel and thick column becomes the building's signature, right? That's the kind of tectonic of the elevation that is expressed. And that is true to the scale of the moment frame behind it. The structure at the Hancock is much lighter, tends to be much thinner. Here, because of those moment connections, everything is just a little chunkier. The tube structure is not just a Chicago invention. It's one that actually springs up in a number of places pretty much at the same time. In New York, the World Trade Centers, designed by architect Minoru Yamasaki, engineered by Leslie Robertson, have a very, very similar approach. They have a stiff steel core that you can see. You can see the moment connections in the core on the left. But the exterior skin of the World Trade Towers was also a bearing wall, essentially, composed of many, 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 many deep columns marching around the perimeter, skinny windows in this case. So when you look at it, like, that is literally a steel bearing wall, right? It functions less like girders and columns and much more like a planar wall. And you can see Yamasaki and Robertson solved the problem of bringing all of that structure down to the base by actually collecting them in these forks that collected the columns, brought them down onto piers, and allowed for significant entry space between them. Other advances in structural types by SOM included what we talked about a little bit when we were looking at Goldsmith's drawings. This is a belt truss system that Kahn and Graham designed for Milwaukee, exposing the trusses that connect the stiff core to the exterior. And because of the triangulation, those trusses create rigid connections that prevent the building from drifting much further than it would otherwise. They kind of reset the building wherever they are and force 90-degree connections to prevent the building structure from racking. SOM also explored the principles that they developed in both Sears and Hancock in different materials and at different scales. So one of the more interesting translations is this one, which is just a few blocks from the Hancock. Onterie Center used diagonal bracing to stay the building against wind. In this case, the plan is like two kind of C channels that have all of the cross bracing and then a center space between them that spans between the two stiff, basically giant C columns. You can see that the way that they get the diagonals out of those is to panelize the concrete frame on the exterior. So it is a concrete grid, but instead of having really, really stiff moment connections, those connections are aided by panels that are blocked off and reinforced structurally wherever those diagonal lines pass through. So this gives the building both the stiffness of a concrete tube, but it reduces the size of the columns and girders by adding the diagonal bracing that you get with the Hancock. Sadly, this was Kahn's last skyscraper project. He died suddenly of a heart attack at the age of 52 in 1981, and was really memorialized as not just an engineer, but also as a philosopher and as a great humanist. He helped run the office in a way that was both intense but also humane. People recall working with him, long, long hours, but in ways where everyone's opinion was sort of valued, and it felt like they were producing innovative work that was kind of worthy of the effort. There were other approaches to skyscraper design and even tube structures within Chicago. One of the more interesting ones was a project by Chicago architect Bertrand Goldberg, who had studied with Mies actually in Germany at the Bauhaus before Mies left for Chicago in 1937. Goldberg remained friendly. He was one of the reasons that Mies ended up in Chicago instead of somewhere else. But he took a very, very different approach to skyscraper design. His earliest skyscraper was this one, Astor Tower, where, as you can see, it is as tightly planned an apartment floor plate as you can possibly get. And it relies on the shear walls in the core for all of its stiffness. To make sure that every apartment had views, Goldberg basically doesn't build the first 5 stories of the tower. Right? The core just rises up, and the lowest apartment floor is actually above the 4-story row house to its immediate north. So you get these very, very long, skinny, unbraced columns that drove his engineer a little crazy, but that worked. And in conjunction with the very, very stiff shear walls around the core, gave the building adequate lateral stiffness. This planning and particularly the ideas about concrete and concrete formwork, this building was in part slip formed, so the concrete kind of grows as the form climbs up the central core tower. These went into Bertrand Goldberg's greatest work, easily his best known work, Marina City, which was built from 1961 to 1964. Marina City was a response to the city's desire to provide much more housing downtown, to help nourish the commercial buildings downtown, the commercial offices, with the clerks and managers, administrators that large companies needed at the time. The funding came largely from a janitors union downtown that also had a financial interest in maintaining the kind of population, the working population downtown, right? If no one lives downtown, the offices, the corporations all move to the suburbs, the janitors don't have offices to clean anymore. So they actually put the money into the project. The city allowed the building to go up on a site that was actually too small for the type of project that they proposed, a mixed use with the 2 apartment towers and then an office building at the back, commercial space on the plaza in the middle, to make sure that it was sort of a win-win-win situation, right? That the janitors union could make a profit, that the city would have this population nearby, and that the residents would have both the convenience of the loop right next door and a kind of unique living situation. The structure of Marina City, though, is genuinely interesting. It, too, is a tube structure. It is built around a giant cylindrical core that provides much of the building's stiffness. But as you can see, that core is monolithic with girders that run out to the exterior of the building. And it has stiff connections with columns that run around between these semicircular balconies. So it has both the kind of stiff core and the rigid exterior of Brunswick, but as you can see, it's designed around a circular plan instead of a square plan. And we know that the hollow cylinder is slightly more efficient, a column shape, than a hollow box. So this is the absolute ideal tube structure going up across the river from some of Kahn and Graham's work. The construction process here was truly extraordinary. You can see the slip form concrete going up on the tower on the right, in the construction photo to the far left. A company called McHugh developed fiberglass forms that now are kind of standard issue technology. They did it to build the complex curvature of the balconies and of those haunched beams that provide the stiff connections at the exterior. And on the right, you see up against a Mies building to the left, that's the IBM tower, the 2 Marina City towers and the office building at the back. And between them, a cinema that was originally planned as a concrete shell roof, but that the contractors couldn't figure out a way to build, and therefore, even though it looks like a concrete shell, it's actually a steel truss roof over the cinema behind Marina City. And Marina City really set a tone, both for bringing people back into the center of the city to live, but also for thinking about ways that structure and aesthetics could be integrated beyond the kind of calm boxes, maybe the simple rectangular boxes that SOM and Mies had pioneered. In some ways, these are very much kind of Bauhaus buildings. They take materials and structure and function quite seriously. You can see that the dimensions are tuned not only to the ideal depth of an apartment, but also, like the Hancock, to the depth of the parking ramps, right? The spiral parking ramps at the base have exactly enough dimension, again, to get a double row of bins in. So there is a kind of functionalism to these, but there's also an expressiveness that is much more about what you can do with the plastic material of concrete than about the rigidity of a steel grid. That kind of breaking the box sees a lot of efforts after the 1970s, especially when a lot of the orthodoxies of the post-war era get challenged, both aesthetics, but also energy consumption and the kind of social life of skyscrapers as well. And interestingly enough, SOM, after Kahn's death in 1981, begins to look more and more at historicist forms, right? They fall into the kind of postmodern approach of looking to skyscrapers past, in particular the skyscrapers of the 1920s, to make kind of relevant urban statements. And here you see a couple of their post-war works. The one in the middle, AT&T, juxtaposed against the kind of rigid box of the Sears Tower. And these are in some ways much more popular, although critics, I think in recent years especially, have kind of looked at them as hedging bets a little bit. Your mileage may vary, but there was also within SOM and some of these other firms a continuation of a lot of the traditions that Hancock and Sears and Inland Steel had started. This is a later project by Bruce Graham, not in Chicago, but instead in London. And in many ways, even though it's a lot smaller than the Hancock, and even though its structural geometry is clearly quite different, in many ways it's a tribute to Kahn. This is an office building that was built over an active rail yard. And the arch, which as you can see is a nice parabolic shape approaching a catenary shape, the arch is expressed in a way that Kahn would have, I think, approved of, right? That becomes the signature of the building, is its structural performance. There's some subtleties to it that you can agree with or not. The fact that the columns below the arch would be in tension and above would be in compression isn't really, there's nothing that really tells you that. But the being able to expose the raw steel in a slightly milder climate like London makes the building a little bit richer in terms of its skin quality than say, the Hancock. Skyscrapers, of course, continue to be with us. We'll look at greater advances in height and in efficiency, but also at the environmental cost of putting so much steel, so much concrete, so much aluminum and glass into one building, and how after the energy crises in the 1970s, skyscrapers become a little bit of an early battleground in the efforts to create more environmentally appropriate solutions to our civic challenges.